So in this last unit that we're covering this year, before we start preparing for our EOC review, we're talking about transformations. In today's lesson, we're talking about translations and reflections. Before we get into that, however, we want to make sure that we're all speaking the same language when we're talking about transformations. First of all, realize that a transformation is, as you can see in the definition, I'm changing where it is, I'm changing kind of what it looks like as far as maybe I'm turning it, or I'm flipping it, or I'm shrinking or expanding it. We'll talk about all of those different kinds of transformations over the course of the next few days. When we do that, the first thing, the original figure, is our pre-image. And then what we end up with is our image. So you might hear me talk in terms of before and after. That's pre-image and image. When the pre-image is congruent to its image, that makes the transformation an isometry. So we talked about, or I mentioned, that we're going to be talking about taking a figure and moving it. If I take a figure and I move it, is that an isometry, yes or no? Yes. The pre-image is congruent to the image. I just moved it. How about if I flip it? Is that an isometry? Yes. All I've done is, once again, kind of move it. It's still congruent. Same thing with if I'm turning it, a rotation. That is an isometry. I would hope that you'd realize just by virtue of my saying it, if I'm shrinking something or expanding something, that is not an isometry. So in problem 1, very, very straightforward. Is this an isometry, yes or no? Yes. The pre-image is congruent to the image. And I know it's listed as a your turn, but let's go ahead and get it out of the way. Is that your turn also an isometry? No, the pre-image is smaller than the image. In problem 2, I have A prime, B prime, C prime. Please be familiar with the way that we talk about images versus pre-image. So let's see. The A prime, B prime, C prime is an image of A, B, C, and we're asked what are the images of angle A and B, and we're asked what are the pairs of the corresponding sides. So what I'm asking you is, what does angle A correspond to in its other figure? A prime. Same idea with angle B. It corresponds to angle B prime. Pairs of corresponding sides is going to sound very familiar. We did this before when we were talking about congruent triangles. It's the same exact idea. Segment AB corresponds to segment A prime, B prime. And you've probably already figured out the other two. Segment BC corresponds to B prime, C prime, and AC to A prime, C prime. So all we're doing here is just kind of laying down the groundwork for the vocabulary we're going to be using in talking about pre-images and images. We haven't actually talked about the first kind of transformation yet. So the first kind of transformation that we are talking about is a translation. And in plain old teenage speak, a translation is just taking a figure and moving it. So in problem 3, I'm asked for the vertices of the image of triangle RST for the translation, and notice the rule that is given to us. that rule is asking us to do exactly what it looks like. I'm going to subtract 3 from the x-coordinate and add 4 to the y-coordinate for each of the points. Now the instructions say graph the image, and you'll see that instruction also in your homework assignment. You'll notice on the board that I indicated that the diagrams are not required, but some of you may find them helpful. I'm not terribly interested in you being able to graph the new image. I want you to be able to, of course, identify where it is, identify the coordinates of that image. So let's first talk about where this pre-image is located. R is located at 1, 2. S at 4, 1. And T at 2, -3. So what I'm asking you is, where is R prime, where is S prime, and where is T prime? Come on, that was almost funny. Okay, so where is R prime? Where is R prime? -2, 6. It's just that easy. You're just subtracting 3 from the x-coordinate and adding 4 to the y-coordinate. So that means that S prime is located at 1, 5, and T prime is at -1, 1. So please take a moment to work through that your turn problem 3. From what I'm seeing and hearing, you're ready to compare your work to mine. You'll notice I went through and labeled where my points are. And then I followed the rule. I added 1 to the x, subtracted 4 from the y, and found A prime, B prime, and C prime. Pretty simple and straightforward stuff. In part B, when it asks you to draw A prime, and B prime, C prime, once again, I'm not requiring any diagrams from you. However, drawing those segments might help you realize the conclusion that we can draw about those segments. Some of you might just see it in your head. What relationship exists among those segments? What is true about A prime, B prime, and C prime? Are they perpendicular? They are congruent. There's something else interesting about them as well. A prime, B prime, and C prime. They're all going from one point to another in the same direction, which means, yes ma'am. Oh, be careful. We don't talk about them being corresponding because we would say that AB corresponds to A prime, B prime. The point that I want you to realize, however, is that they would be parallel. A to A prime, B to B prime, C to C prime, they would be parallel. And we have from this screen what we need? You guys are good? All right. Teamwork. I love teamwork. Okay, how about working backwards? If I have the pre-image and image, can I come up with a rule that describes the translation? Make sure that you're making your rule look the way they did. You're doing something to the X and Y to move them. Make sure, and here's another common mistake that could happen. Be very careful about which one is your pre-image and which one is your image. Which one is the original? The one without the primes, absolutely. So do I have to figure out what is happening from L to L prime and from M to M prime and from N to N prime? No. Because why? Say that again, I'm sorry? Right, so I think what Jesse is saying is that the rule from L to L prime would be the same, absolutely, as the rule from M to M prime, N to M prime. Why do it 3 times and just get the same answer 3 times? So let's identify where L is. It's at -5, -4. And L prime is at 1, -1. So what's happening to the x's, what's happening to the y's, and what, therefore, is our rule? I'm adding 6 to the x and 3 to the y. There's our rule. What a great way to end the year. And take a moment and work through the your turn problem 4. From what I'm seeing and hearing, you're ready to compare your work to mine. If there's a discrepancy, if there's a confusion, let's make sure we talk about it before we move on to reflections. Wonderful. Okay, so in plain old English, you get the idea that taking a figure and reflecting it over a line flips that figure over. The textbook wants to be really, really specific about what goes where. So one point that I want to emphasize, and it does, this explanation does help us be able to do problems like this next problem 1 without necessarily having to draw a diagram, if you kind of get the idea of what's happening mathematically in a reflection. Okay, so if I have a point P and it's being reflected over line L, here's my point P. When I reflect point P over line L, my point P prime would be, let's say, about here. Couple of things I want you to notice about P, P prime, and the line L. Notice that when I connect P and P prime, what do you notice? What do you notice about the red and blue lines? Yes, ma'am. It is perpendicular to my original line. And do you also see that that line of reflection is bisecting the segment connecting P and P prime? So put another way, the distance from P to the reflection line is the same as the distance from the reflection line to P prime. Okay, so I want to take that into consideration when we reflect this point over this line without drawing it. Okay. First of all, what kind of a line is y equals -3? I would hope that you'd remember from algebra, either a horizontal line or a vertical line, but which one is it? Remember which one it is? It's y equals, and that's what your gut instinct wants to say, but you've got to remember it's actually horizontal. And if that's not something that you knew instantly, you probably want to jot that down. Okay, just a reminder to yourself. If you have an equation, y equals a number, that's horizontal. Whereas if you have an equation, x equals a number, that's vertical. That wasn't something that you already knew instantly. It's probably something you want to jot down. Okay, so I'm taking this point and I'm reflecting it over a horizontal line. So visualize it. My line of reflection is a horizontal line. Does it make sense that one of my coordinates is going to change and one of them is going to stay the same? Okay, so I have a point, I'm reflecting it over a horizontal line. Which coordinate is staying the same? Which coordinate is staying the same? The x coordinate or the y coordinate? If I'm flipping it up or down, which coordinate is staying the same? Oh, the x. Because am I changing horizontally, which is your x coordinate? No, I'm not changing horizontally at all. So since we're reflecting, over horizontal, x stays the same. So I know my point is 2 comma something. And then I got to figure out what that 6 is going to turn into. Remember what I told you up here. However far away my point is from my line of reflection, that's how far its image will be from that line of reflection. So here's a question to you. I know my point is going to be 2 comma something. How far away is 2 comma 6 from my line of reflection? How many spaces away from my line of reflection is 2 comma 6? It's 9 spaces away. Realize which numbers you're comparing. What kind of a number is this? It's a y number. So compare it to the y number. Okay, it's 9 spaces away. So I'm going to go 9 spaces in the opposite direction. What is 9 spaces in the opposite direction from -3? It's going down, right? So I heard it, -12. Now, of course, I realize some of you kind of conceptually might get this while I'm yammering in your ear, but when you get home, that 2 comma -12 is, you're going to forget where it came from. Okay, so you might want to add a diagram to your notes so that you see where it came from. Okay, my point, 2 comma 6, is somewhere up here. Here's my point F. I'm reflecting it over the line, y equals -3. So let's say it's here. This distance, remember, we realized that this distance was 9 spaces. So that's why we went another 9 spaces to get to -12. Yes, ma'am. Okay, so let me make it a little bit more perfect. Okay, my line of reflection was y equals -3. Here. My point, was 2 comma 6. So that was here. Do we visually see that from this point to this line, there are 9 spaces? And now do you see why I'm going to go 9 spaces in the opposite direction? Wonderful. Okay. In problem 2. Oh, wait. I missed something. There was it your turn. And you know what? In the interest of time, let me get through problem 2, and then you can your turn problems 1 and 2. I'm completely forgetting what my notes look like. Sorry. Okay. All right. In problem 2, I am taking these points, x, y, and z, and reflecting all of them over the x-axis. So the x-axis, remember, is a horizontal axis. And since I'm reflecting over the horizontal, what coordinate is staying the same? The horizontal. I'm flipping it over a horizontal line. My horizontal coordinate stays the same. So I know x prime is -4 comma something. I know that y prime is, yes ma'am. Because, remember, back here, since I'm reflecting over a horizontal line, what's changing is my vertical orientation. If the equation is x equals a number, that's a vertical line. The x-axis, however, is your horizontal axis. And I get it. It's counterintuitive. It goes completely against what your gut instinct wants to say that it is. You've got to be careful to keep them straight. All right, so I know y prime is 2 comma something, and I know z prime is -1 comma something. Now here's the beautiful thing about reflecting over an axis. Well, the x, say it again. Exactly, the sign is all that changes. So I know x prime is -4, +3. I know y prime is 2 comma -6. And I know z prime is -1, +8. Okay, so if these are little tidbits that you want to add to your notes so that you can do these things more quickly, feel free. If I'm reflecting over the x-axis, x stays the same, and y, take the opposite. So if I'm reflecting over the y-axis, the y stays the same, but the x is the opposite. Beautiful. Take a moment, work through the your turns for those, please. Okay, let's go ahead and get started talking about these your turns. In this first your turn, realize that because x equals -1 is a vertical line, visualize it. I'm taking a point and reflecting it over this vertical line. My vertical coordinate is what's staying the same this time. Okay, so if you want to jot notes to yourself so that you remember what we did, since x equals -1 is a vertical line, y stays the same. So I know my answer is going to be something comma 4. Here's a tip. Here's a tip. The variable in the equation is the one that's changing. Okay? So if I have an equation, x equals a number, that's a vertical line. My equation is x equals something, x is what's changing. Because x, that -1, is what I'm comparing to 3. Figure out how far apart they are. So how far apart is point P from its line of reflection? How far away is point P? It's 4 spaces away. You're looking at how far apart is positive 3 from negative 1. It's 4 spaces. I need to go 4 spaces in the opposite direction. Casey. Remember that think about it this way. From 3 2, 1, 0, negative 1. Okay, when you're counting the distance, remember, when you were born, you were not 1 year old. So you don't count the 3, you go 1, 2, 3, 4. Good? And that's the common mistake is people count the beginning and end point. Don't do that. Just want to make this go away. Okay, so it's 4 spaces away. So I need to go 4 spaces in the opposite direction. So I'm going 4 spaces to the left of that reflection line. Okay, here's my reflection line at negative 1. What's 4 spaces to the left of it? Negative 5. Once again, because from this x of negative 1, my line of reflection, to the x coordinate of my point, do you see that that's 4 spaces? Say that again? Okay, let's look at it visually again. Okay, and again, gentlemen and ladies, there is no shame in being a visual person. I'm a visual person. Okay? Let me put a grid on here. Okay, so my point is 3. Where'd it go? My point is 3, 4. And my line of reflection is x equals negative 1. Now, it's a little wobbly, but do you visually see that this point is 4 spaces away from that green line? Okay, so I'm going to go 4 spaces in the opposite direction. This blue point is to the right of my line of reflection, so I'm going to go to the left of my line of reflection. What's 4 spaces to the left of that negative 1? There's the negative 5. And then in problem 2, we are taking that triangle and reflecting it over the y-axis. So in problem 2, you have, where'd they go? These 3 points. Remember what we talked about. If I'm taking a point and reflecting it over the y-axis, the x is what's going to change signs, and the y is what's going to stay the same. So, for that your turn problem 2, what you should have had is x prime at negative 4, no. Yes. What? I got it backwards, didn't I? I'm sorry, I'm reading the wrong problem. I'm flipping it over the y-axis. So, 4, negative 3, y prime at negative 2, 6, and z prime at 1, negative 8. Last problem. In problem 3, kind of an application of reflections, I'm trying to minimize the length of my irrigation line. My irrigation line needs to go from the corn to the river and back to the beans. Well, where on earth would reflections come in if I'm trying to find the shortest amount of irrigation line to use here? How can I use reflections to find the shortest amount of irrigation lines? that I'm using to go from the corn to the river and back to the beans. What's the shortest distance between 2 points? Shortest distance between 2 points is a straight line. Okay? So, if I take these beans and kind of reflect them over the river, what's the straight line from corn to that reflection? So that point at which it's hitting the river is the point that minimizes the length of my irrigation line. This black line is how to minimize my irrigation lines, which is kind of a real-world application of reflection. Why would reflection? Well, because some of you are kind of deer in the headlights. This is congruent to this. And if the shortest distance between 2 points is a straight line, then I have just created the shortest distance from the corn to the river and back to the beans. The assignment is on